Welcome back, everyone, to Engineering Made Short. Today we're going to be going over the Fourier Transform. This is honestly one of my favorite mathematical principles and theorems, and when I first was taught it in my classes, I was like really completely lost as to how it works. But when I understood through a lot of research on YouTube, uh, I finally really appreciate it. So what is the Fourier transform? Well, let's get into it. The Fourier transform is simply a mathematical transform that shifts signals from the time domain to frequency domain. On the left here we have the time domain. Effectively what the time domain is, right? It's like how we plot functions. It plots the voltage or amplitude, right, versus time. So it plots y of t or voltage over time. So here we can just see normally we have, let's call it a sine wave at some arbitrary singular frequency. Let's call that frequency 50 hertz, right? We can clearly see it's a sine wave. Now we do our Fourier transform and boom, we get the frequency domain. The frequency domain plots voltage over frequency. So let's say the way I like to think of it is a sifting plot. It tells you what frequencies at which amplitudes make up our signal. So here we can see there's only one singular non-zero contribution at 50 hertz. Well, that makes sense. Our sinusoid is a singular sine wave at 50 hertz at a finite amplitude. So it effectively sifts out the function and tells you what frequency components are made out of this function. So with this being said, right, what are the applications of Fourier? Why do we care about this transformation in the first place? Well, one, it's really helpful in audio and imaging processing, right? Let's say we have a file, an audio file that has a super large amount of noise or background sound, etc. Well, we can take the Fourier transform, see what frequency those noises are happening at, and remove them, delete them, process them better, etc. Right? We can do a filter, for example. We do a high-pass filter, take out those high-level noise frequencies, and boom, a lot of that noise is gone. In fact, we actually use this during and after World War II. We created what we call the fast Fourier transform. It's just the name, it's a faster Fourier transform to decrypt adversaries' communications and help encrypt allied ones. So it's really helpful. Secondly, from a mathematical perspective, it allows us to convert differential equations to algebraic ones. If any of you are taking diff-EQ, stay ready, be prepared. It's going to get a lot easier after you learn it, right? And we know differential equations are simply equations consisting of first, second, third, etc. derivatives, and that's hard to calculate, right? To find why this is hard. So now, if we have Fourier, well, boom, we can use x is equal to negative b plus or minus the square root, etc. to just solve the algebraic one. So it's really helpful from a mathematical perspective. So before we actually get into transform now, we need to go over two things. The first is Fourier principles, right? What are the mathematical principles that help us conceptualize and understand why Fourier works? The first one is that any signal or function can be represented as an infinite sum of sinusoids. In other words, let's say we have right here a square wave, right? This is what we're trying to approximate. That square wave can be made up of an infinite sum of weighted cosines or sines, right? So visually, this is how it works. Here, we're adding different sine waves of different amplitudes and different frequencies. And once we add them together, right, we slowly see that this original sine wave becomes a lot more likely and a lot more shape-like of a square wave, right? And the theorem goes is that, as we can see, as that sum of, sine waves approaches infinity, right, that square wave becomes ever more perfect and ever more square, right? Of course, it's not going to be 100%, but it's an approximation, right? You're going to have these little spikes in amplitude on the side. The second is Euler's rule. This is very simple, right? E to the j omega, right, is equal to, and e to the j omega being a complex exponential, is equal to the sum of cosine omega plus the complex number j times sine omega. So we can basically represent any cosine or sine term or combination of them as a complex exponential. And just as a kind of descriptive addition, right, omega in this case is frequency in radians per second, right? We can see right here at the bottom, not meant to jumping ahead, but anyway, omega is equal to 2 pi divided by the period t, The second thing, of course, is j. You've probably seen this number in a lot of math classrooms as I, right? It's just an imaginary number. So that's why we call it a complex exponential. It's e to the complex exponential j times omega. So Euler's rule is the last principle. Secondly, like we said, is how can we visualize how that sum works? Well, that is the Fourier series. There's two parts to the Fourier series. The first is what we call the synthesis equation. The synthesis equation is the infinite sum, right? We can see right here, of the weighted sinusoid, and that equals the signal we're trying to find, x of t. So a sub k is the weighted constant, right? Like we said, every signal can be made out of a weighted sum of sinusoids. So to determine that weight, we have a sub k. And then the second thing, of course, we have here is e to the negative j omega t, and that's simply the complex, exponential, which again, if we want to move around, we can reconvert into a combination of a cosine and sine term. So the synthesis equation is just telling you that we can infinitely sum these weighted sinusoids to equal x of t. And now, the natural question that comes next is, okay, well, how do we determine what a sub k is? That's simply the analysis equation, right? And all it's saying is we're going to take an integral over one period of the original function x of t and multiply it by this, or technically a better term is to convolve it by this term e to the negative, jk omega naught t, and the integral of that function is basically going to be our constant, a sub k, right? And naturally, right, if we do this for different periods of x of t, right, as the function oscillates, the value of a sub k is going to be different. So the analysis function gets us the weighted constant a sub k, and the synthesis function tells us that if we multiply that by the complex exponential, sum that over infinity, boom, we have x of t. Okay, so with that being said, we now can get to the Fourier transform, right? This right here, top one, the big kahuna, is it in its entirety, Fourier transform. We represent the functions in the Fourier domain as x of jw, or whatever other term you can do, capital Y, capital Z, whatever it is, capital X of jw, and the integral is the infinite integral of x of t convolved with the complex exponential, where x of t is our original function and e to the negative j omega t is our complex exponential, and that is integrated over time. So the quick note here is that the Fourier transform only works for stable signals, right? Stable signals are signals that if there is a bounded input, there would be a bounded output. There's two reasons for this, and I think the second one is the most important. The first one, of course, is just mathematically speaking, right? In order to do this integral, the term inside of the integrand needs to be absolutely integral, right? That's pretty logical, that's pretty intuitive. But the second one actually tells us why, right? As we can see here, our complex exponential term only contains a complex part, right? So effectively, it's e to the 0 plus or 0 minus j omega t. And that's important because let's say x of t is an unbounded function. Let's say x of t equals e to the 2t, right? It's increasing exponentially. Well, since e to the negative jwt doesn't actually have a real part, there is no way that we can dampen, limit, or prevent this from going and being unstable into infinity, right? So you've heard the term before probably in your physics classrooms with dampening. That's the issue. There is no real part of the complex exponential to dampen the real part of x of t. So as a result, there's a necessary precondition where x of t has to be a stable function. The bottom one here is just intuitively the inverse Fourier transform. We'll get to this in another video because inverse Fourier requires an extra theorem that makes this, really weird looking integral quite easy. So that is the Fourier transform. Let's get to an example. Let's say, we're chilling and we want to determine what is the Fourier transform of x of t is equal to e to the negative t u of t. Quick, easy thing to do is first let us jot out what x of t looks like. basically it just looks like this, right? E to the negative 2t is a decaying exponential, and u of t, right, is the unit step function. Just as a reminder, the unit step function is the function that turns on at t equals 0 and is on to t equals infinity. So what this means is we have a decaying exponential that only begins to decay at time equals 0. So obviously the first question we ask ourselves is, can we do the Fourier transform on this function? Well, the answer is yes, right? E to the negative 2t is a stable function because it declines over time. It's a decaying exponential. All decaying exponentials are stable, right? They approach 0 as time approaches infinity. So that is correct. So let's get into the integral now, right? So we set up the integration, right? We have the infinite integral. This is our x of t, right? E to the negative t u of t, and then of course this is just the rest of the integral, complex exponential. Okay. First simplification we can do is we can kick out u of t and fix the bounds of the integral, right? U of t, the unit step, tells us that this function only exists for time t equals 0 on. So we can take out u of t, and instead of having negative infinity, we have now 0, right? Because the function does not exist for time t is less than 0. The second is just a quick algebraic manipulation, right? With our exponential rules, exponent rules, we can simplify those terms so it's t times this complex number here. Now, using u substitution, which all of you should probably know if you're watching this video, right? We can take out the constant, right, by dividing out 1 over negative 2 minus j omega. Then we have this really simple integral in here, e to the u du. We all know that the integral of any e to the t, e to the u is simply just e to the t, e to the u. So at part 4 here, we have this, right? We have the constant 1 over negative 2 minus j omega multiplied by e to the u ranging from infinity to 0. So let's expand, let's solve, let's do it quick. So when we expand the e to the u term, we can first, of course, have to take the limit. I'm just using a dummy variable, let's call it tau. So the limit of tau as tau goes to infinity of e to the tau times this is, simply just going to be, is simply just going to be 0, right? Because this is a negative real component, and as we multiply this negative component by infinity, it's going to be going closer and closer and closer to 0. And then we have the second part here, right? It's e, where now our u is equal to 0, and of course any number raised to the power of 0 equals 1. So our resulting answer is 1 over, taking out negative 1, negative 1 times 2 minus j omega, and then times just, right, negative here, or negative 1. So when we do that, the negatives cancel, and beautifully we have 1 over 2 minus j omega. And number 5 here puts it all together, right? The answer to our Fourier transform of e to the negative t u of t is 1 over 2 minus j omega. So that's a very basic integral, one of the most basic Fourier transforms you can do, but really does underpin quite a lot. Again, thank you all for watching, and this has been the Fourier Transform on Engineering Made Short. I'll see you all next time.